Okay, so I understand that we all are already tired, but I will try to be as quick as possible, and I will show mostly pictures, and since I'm a physicist, so I will not prove the theorems. So it's the talk consists of two parts, and the first one is the reminder of what is known on the border between mathematics and biology, and everything is related to random walks and topology of knots. And so the second part is something our new achievement in the field, and you will see, so these two parts are complementary. Suppose that you have random walk, which is very long, and you put it in a small box, and you ask, so you shake the box, and your trajectory is closed, and it forms the trivial knot. You ask the question, what is the fractal structure of this long trajectory in a small box? Yeah, so that is the random walk can be characterized by the fractal dimension. Okay, so and then, so this is the first part, and I will give some reminder of what is known. And the second part, which is recent, is the, I would say, sufficient and necessary conditions. So the second one is the inverse question, the reversed question. So suppose that you know that you have some fractal dimension of the random walk. Can you say anything about its topology? So, and so these two parts are complementary. So, and so let us proceed. And first, we pass from topology to fractal structure, and we ask this question. What is known? So everything is related to real life, to real physics, and basically is motivated by, okay, so it depends. Historically, these questions were asked independently, but now from just sitting and saying downstairs, we see how they are arranged during the time. So, and we can start with the following. So DNA, yeah? So it's molecule 2 meter longs, 3 billion base pairs, and it's packed in very small capsid, so known as nucleus of the cell, and it's 2 micrometers, 20 micrometers in average. Yeah, how? So now what we have? We have this very dense, long molecule, and we should somehow read the information taken from, take it out from it. So what is that? It means that, so you should take part of this long chain out of this small ball. So then you put ribosome which runs around it, reads the information, and then this part goes in again. So, and this process should be done reversibly and very fast. How you can pull out, so for instance, if you have just wire and it's highly tight, highly linked, yeah, so you have many knots in it, so you try to pull out some part of it, and it's almost impossible. How we can do that in real life? How to do that quickly and reversibly? So probably everything is related to special kind of folding, and what was known the classical theory of so-called coil-to-globule phase transition. So it means that you have, what does it mean? So coil-to-globule transition, it means that you have very long random walk with some interactions. So then you make some, for instance, attractive interactions bigger. So, and your long trajectory gets collapsed. So it's like a phase transition. Like localization transition. So, and it forms weakly fluctuating small drop, and this is called globular phase. The theory of that was elaborated during these years, mainly in Lifshitz, Grossberg, Khokhlov works, and here in France by Dejean. I don't know what something was skipped. Okay. Yeah, at low temperatures, the macromolecule, so this random walk, forms compact, weakly fluctuating drop-like structure. And now this is a question. Okay, so everything what was known is known for long, open, long random walk, long chain with open ends. And now let me ask the following question. If I close the ends from the very beginning, making this long trajectory closed, and then as I put it in a small box, will the fact that it's closed and not knotted affect the internal structure? The answer is yes. And in principle, there are two options. So suppose that this is a small ball, and so then inside it, what could happen? So it could be just a kind of melt made by this molecule. So different parts can penetrate into each other, highly entangle themselves, link, and so on. Or another option is that on all scales, from very small one to bigger ones, the subparts, subchains stay separated from each other. So they are segregated in space. And in fact, so the difference is that different chain parts penetrate into each other. Here, no. And which scenario is realized? So it was not known. And in fact, I will show you that in this situation actually holds. And how we can construct it. First, I will try to describe it recursively, and then I will say some words which explain why it is stable. So suppose that we start, so we have very long trajectory, and then we start folding it. So first what we can do some small crumples, like shown here. So now this long trajectory is like a sausage. So then I make sausage of sausage, and then I proceed further. Yeah, you see we have folds on all scales. And finally, I have in the space something which resembles piano curve. Yeah, because it's compact in all scales. So this part stays segregated with this part, while this blob is segregated from this one, and so on. Yeah, different scales, they stay separated. So you see that actually this structure has hierarchy. So it consists on levels of different scales. And what was known since 2009, so this was the numerical simulation, first real experiment about which I will not tell now, and numerical simulations which actually show that the structure, the compact structure looks like that. What are the colors? What this picture represents? Suppose that you just make your polymer like a straight line, and then you paint it from one end to the other one in continuously changing color. So here is blue, here is red. Yeah? So, and then this picture shows you that the monomers which are close along the chain are close in the space also, close to each other in the space also. That's why you can see the territories. So for instance, I don't know where is the end, probably here is. Yeah? So it's so this is the beginning of my chain. So it's blue part. And you see that blue parts, so they are blue in color along the chain, so and they stay near each other in the space also. So this is exactly the structure which looks like that. So on different scales, monomers neck boring along the trajectory stay close to each other in space. Okay, this is kind of, so this is numerical simulation, but how we can guess that this is stable, how we can, at least not to prove, but to conjecture why it survives. That is just a small reminder how it looks like, and this, you know, so this is like doshirak, fast food, and in fact, it's not a coincidence that it looks like that, because you know that if you add water here, so then the crumbles which are outside just expand and allow water to go deeper. So it gets wet very quickly. Okay, so let us start with the. So sometimes I skip slides. Okay, so let us start with the quasi two-dimensional case, because this is simpler in some sense, but captures the main ingredients of the model. So what I have, suppose that I mimic my dense configuration by a lattice knot. So here is the knot projection, so knot diagram, which so this is closed trajectory, so the single loop, and what I have done, I'm putting randomly in each intersection, so the index which labels me, which labels whether it's upper intersection or lower one. Yeah, so I randomly create such carpet. So, and then I can ask, for instance, what is the typical complexity of this knot? And so there are different ways how one can characterize the complexity of the knot if we follow the analytical methods. If we use analytical methods, so then we can define the algebraic knot invariant. For instance, this could be either Jones, Kaufman, Alexander, any way we want. So, and then we take the degree of this polynomial, and this degree, in some sense, captures the information about the knot complexity. If n is small, so the knots are not very complex, n is proportional to number of vertices in the lattice, so then the knot is sufficiently complex. So, and two more remarks, so that degree n defines the metric space and allows to range the knot by complexities, because we can say, just computing this n, we can say which one is more complex, which one is less. And also, because all, at least these known algebraic invariants, so they are like a can be written as a partition function. So the logarithm of the partition function has a sense of the free energy. So we can associate, we can add some physical sense to this quantity. But if we would like to proceed simpler, so then in numerical simulations, the complexity can be characterized by minimal number of intersections. So let us look how I can simplify this knot. So you see, I just reduce according to Redemeister moves. So this knot. So, and then what I get is the minimal number of intersections, and in this case is number 5. Yeah, I can characterize knots just computing the minimal number of crossings. Okay. And now I can ask the question like in the way I'm interested in. Suppose that I have a trivial knot. So it means that suppose that I'm so clever that I have constructed this lattice in such a way that the knot, so this is unknot. So this is completely reducible knot, so it's trivial one. Yeah, but of course, any part of it, so even looking at this diagram, I cannot immediately say that I can reduce it. Okay? What I do? Now I cut part of knot and I reclose ends. So I eliminate the red part and I reclose the ends like shown here. And I ask the following question. Under the condition that my former construction, the parent knot, was trivial, is it true that this guy is trivial as well? Or at least more trivial than it would be without this condition on the parent knot? Okay? And this is exactly what I need, because I want to see that any part of my huge loop is unknotted, yeah, or at least almost unknotted. And in fact, this is true because this we can do either using some kind of applying Jones polynomials, or we can use this numerically. Let me just give you the answer. The answer is like that. I don't know what is. Yes. The answer is like that. Unconditional complexity. So if I just randomly put upper and under crossings, gives me very highly knotted configuration. So you see that typical complexity of randomly created knot diagram is of order of number of intersections. So it's of order of n. But if I say that, so this is unknot, I remove some microscopic part and I reclose and look for the complexity of the rest. I see that it's square root of n, so and relative complexity is negligible. Yeah. So any part of unknot is weakly entangled. So that's is this message.
That's in dimension 2.
It's in dimension 2 plus epsilon. Yeah, but the simulations, and I will show you. So this, the simulations have been done in dimensions 3, and so these are in this work. So they have been done in this work. So these are real simulations, and you see that there is a signature of territories here. So this is fractal dimension 3. Fractal dimension 3 is the fact that the monomers, as I said, stay close to each other in the space. So it means that the fractal dimension of the trajectory coincides with the fractal dimension of the space. So here you see territories, here you see no territories. So this is the fractal dimension 2 as usual random walk. Here is 3. Okay, so I will not tell about the experiments, but this, I would say that this is confirmed in Harvard MIT so-called experiments on widely genomic capturing chromosomes method. Okay, now let us go back and ask the question which is complementary. If we generate somehow the fractal structure which is of the polymer, in our case d equal to 2 is the polymer which has the fractal dimension of the random walk. This is not interesting for us. But we would like to have something more compact. So our goal is 3. So for instance, if fractal dimension is 3, is it sufficient to have to see conformations which are less knotted than it would be for fractal dimension equal to 2? And why is important? And there are different reasons. One is just the kind of technical one, because if we can replace, at least partially, the topology by just fractal dimension, so then we gain essentially the speed of computations, because topology is something which is very non-local, yeah, and it's very difficult to describe random walks with topological constraints and so on and so forth. But to keep the proper fractal dimension is much more simple situation. So, and now the question. The first is the following one: how to generate the random walks with the fractal dimension bigger than 3. Bigger than 3, I remind you, so it means that the trajectory is more compact than the random walk. Yeah, so it's more dense. And the idea is the following: the typical random walk is so you see that you have interaction. So this is the contour length of the chain. Yeah, so this is the loop. Yeah, you see. So and black lines. So these black springs are nearest neighboring interactions which are present. So these ones. So these are in fact, when you go to the continuum limit, you produce the Wiener measure from that. But now we add more distant interactions. So we have not only nearest neighbors, but this one, so then this one, but the strength of this interaction is weaker. So you can imagine that we have just strings with we have a network. We have not anymore the random walk. We have a network where everyone interacts with everyone, but the strength of the interaction, the spring constant, depends on the distance between monomers along the chain. So, and we can select, so this is exactly computable case, and we can link this power in this decay with the fractal dimension we want. So this is the mean square distance between ends, and you see that fractal dimension we can generate, any fractal dimension we want, we can generate by properly adjusting this exponent gamma. So by this way, we can generate any trajectory which is compact, less compact, more compact, and so on. So, and now since we have this tool, we can, just one more thing. So in the continuous limit, what does it mean? So if you go from discrete action to the continuous one, so then it corresponds not to the just Brownian motion with the Wiener measure, but you have non-local kernel. So these are the standard. So if this would be delta function, so then you will have just x over xi squared as standard Wiener measure. But if you have this kernel, so it's non-local, so and if it depends in special way on this distance, you can mimic any behavior as I said. So this is nothing special, but just kind of continuous situation. Okay, so and now the answer. So here are snapshots of different configurations when corresponding to different fractal dimensions. So this is 2, this is standard random walk, this is slightly more compact, this is even more compact, and this is of our interest. So, and the final, okay, so this is, these are snapshots. So in the bounding box, you see here is the, so this is the critical exponent. We need something like 1/3, so 0.33. So you see that this is, so we clearly see the so-called territorial organization. The colors represent the same as in the first part. So, and you see that if I continuously go from the random walk to much more compact situations. So I see a proliferation of this territory structure. Okay, so and the last slide is this one. I don't know why it's invisible. Okay, so to compare knotted configuration, so now this is purely numerical part. So we just computed the huge number of different configurations with prescribed fractal dimensions, and so then computed the knot complexity, just taking the standard thing, which is Alexander polynomial taken on special value. So, and we discriminate topologies by this by this function. So it's standard 2 in statistical physics. Of course, it's not precise, of course, but at least it's sufficient for all our needs. And what you see here? So you see that you have very broad distribution if you have standard random walk, and distribution in knot complexities is very broad. And if you go slightly to much more continuous step by step to more dense configurations, so you see that the number of different knot topologies changes drastically, and it gets concentrated on rather weakly knotted configurations. So it means that actually, if we follow this way from the fractal geometry to topology, we actually see this coincidence. So on one hand, compact Brownian path with fractal dimension are less knotted than ordinary. So, and this provides possible tool for mimic chains with topological interactions without explicitly taking into account the very complex machinery of working with knot invariants. So, and probably this is the end.
Let's thank you. Questions, please.
Chochlov was your supervisor. He's a supervisor.
Sorry? Yes and no, yes. All persons mentioned there were, in fact, I was just person working with many of them. Yes.
Maybe a naive question.
Yes.
And a part of Alexander polynomial, other polynomials appear in this?
Yes, as I said, everyone can use. Just one thing which is maybe explains where is the mathematical background of this. Why the part of, so as I said, the main ingredient is that if you consider the unknotted configuration and then you can look for the part of it and look for the topology, it's less knotted, yes? To what it's related? It's related, in fact, to the following. So, and this goes back maybe also to Anya's problem. Consider the product of random matrices. These are unimodular 2x2 random matrices. So, and then what is known, there is a Furstenberg theorem which tells you how the highest eigenvalue of this product grows. It's exponential, yes? But now you say, okay, we impose the condition that we have a kind of Brownian bridge. So it means that we say that this configuration, this chain is identical to 1. So in the language of topology, it means that I say that my the whole configuration is trivial knot. And now I ask the question: what is the probability? What is the how grows the, say, subpart of? Sorry, here should be square root of n. So and it grows like square root of n. So under the condition of the Brownian bridge, any subchain grows much with less speed than than in the unconditional case. And that is the origin of all these topological effects we found.
Other questions?
Yeah, so the key ingredient is then just the Brownian bridge for the Brownian motion on the hyperbolic.
Yes, right, absolutely. No hyperbolic. You can imagine that you have, for instance, Lobachevsky plane, and you do two things. One, you have, or even three. Okay, so you have two things. One, you just look for the unconditional random walk on the tree, and you look where is the end of this chain. And of course, it goes just linearly with the number of steps, because you have more probability to go away from the origin and less to go back. And now you ask the question, okay, let me make a Brownian bridge and ask what is under the condition of the Brownian bridge, how distant is the medium point. And it goes with square root of n. In some sense, by Brownian bridge, you kills the curvature.
But you also need some tools to vary the fractal dimension. How do you do that?
Yes. So the fractal dimension we vary in this way. Here it was.
Well, that's theoretical. I mean, how do you generate?
So that's the way to generate. We just used this action, just putting it in the computer.
Yeah, but my question is about the algorithm that the computer uses. Is it some kind of Monte Carlo simulation?
Yes, it's a Monte Carlo simulation. Yes, it's a Monte Carlo simulation. Right. It's more or less the same as you generate the random walk. Yeah, you generate it step by step, but here you generate it not only having step-by-step condition, but you know where is the not nearest neighbors interaction, but the nearest neighbors interaction, and so on and so forth.
But this is not a Markov.
It's not a Markov. It's not a Markov chain. But still you have the adjacency matrix. You can just generate the full matrix, and that's it. You can easily write down the adjacency matrix, which will be not 3 diagonal, but it will be distant.
That matrix will be like million by million.
We generated up to 20,000 by 20,000.
Wow.
Okay, if there are no other questions, let's thank speaker again and all speakers of today.